welcome everybody. Welcome, Chris. I will introduce you in a bit more detail in a while. But for the moment, I just want to share with you, for those who have not seen this before, just a little bit more about Cement and Concrete SA. And maybe I should get back to the beginning of the presentation. That might be a good idea. Our partner members, AfriSam, Lafarge, PPC, and Sapaku. Gold member Creso, silver members, Geoli Readymix, CoreStruct, Quick Group, Sika, and SNA. And then with great appreciation to all our bronze members, and we're going to go through a few screens of their logos. So welcome to everybody. Our emerging contractor members, we're very pleased to have this category, and welcome to everybody from those categories. Our associate members and our academic members. And then, as you all know, we're an international partner of the American Concrete Institute. And then just a reminder that we are now a voluntary association of the Engineering Council of South Africa. So please remember, when it comes early next year, time to renew your membership, you can actually claim 1 CPD point for your membership of Cement and Concrete SA, and you can get a discount on your EXA fees. What's new? You might have seen our new leaflet, Know Your Cement in the Interest of Safety. We've become aware of many unscrupulous cement sellers, cement suppliers, especially in our rural areas. So we're really embarking on a campaign to tell people what ought to be on an authoritative bag of cement by law in South Africa, what you should be looking out for, and where to find it. And then something else, the save the date for our Concrete Working for Water roadshow that will happen at the end of February next year. Our speakers are all confirmed, and bookings for this event will open shortly. The latest issue of Concrete Baton, the November issue, is online in its usual digital format. Please read it. It is available on our website. And then the new education program from our School of Concrete Technology is also available on the website. Please have a look at this. Remember, we're always building a future together. So I'm going to stop sharing this screen, and then I'm actually going to introduce our speaker for today. I'm very grateful to Edwin Trout from the Concrete Society in the UK, who actually gave me the contact for Professor Chris Goodier. And I really am happy. I said to him in an email, it is lovely to work with somebody who's as responsive as he is. I send a mail, 5 minutes later, I've got my reply, and we were communicating one evening. I think it was 9 o'clock our time. It was 7 o'clock his time in the UK, and we kept on communicating, and how lovely. And immediately he responded, yes, he's prepared to do this talk for us. Particularly since we've become aware of the problems with autoclaved aerated concrete in the schools in the UK, and it was hugely publicized. In the technical committee of Cement and Concrete SA in South Africa has urged us to look at something that we in South Africa must just become aware of potential problems, aware what the problems were, and so that we be aware of it and maybe take precautionary actions. So let me introduce you to Professor Chris Goodier. He is Professor in Construction, Engineering and Materials at the University of Loughborough in the UK. He's Director of the Academic Staffing and Development, as well as of the Centre for Innovative and Collaborative Construction Engineering. He's also part of the senior leadership team in the School of Architecture, Building and Civil Engineering. But I think more important for us, he's a member of the Concrete Society, a fellow of the Institute of Concrete Technologists, and he's been leading the UK's research into reinforced autoclaved aerated concrete. Following an announcement not to open some schools containing that earlier this year, concrete was in the media spotlight like never before. And he's been leading the research funded by the National Health Services as a member of the Institute of Structural Engineers, and he's been advising numerous government and industry parties on the properties of reinforced autoclaved aerated concrete and how it's very different to conventional reinforced concrete. So, Chris, we're keen to hear what you're going to share with us. You've got the facility to share your screen. Please, you can go ahead.
Great, thank you. So I'm sharing my screen now, and presuming you can hear me okay.
We can hear you, thank you, and we can
see my
your
face,
screen.
the only face I've got. Thank you for the invitation and the very nice introduction, and nice to meet you all, even if online. I did visit South Africa 10 years ago, Cape Town, as many people, and spent a couple of weeks there for a conference and a bit of a holiday. And I know they are very active in the concrete in the world, and there's a lot of concrete conferences that are often in South Africa, particularly Cape Town. So I know you are one of the leaders in concrete technology, which is why it's nice to be asked to do this talk and to talk to some like-minded individuals. So I was introduced there. The way I describe myself is a civil engineer. That was my training. I was a contractor for a few years, built a lot of things in concrete, bridges and tunnels and motorways. My PhD was in concrete repair, which got me interested in that. I worked for BRE, a consultancy, for 4 years on concrete inspection and repair. So very much, I'm an academic and do a lot of research, but my background is very much wedded in industry and real buildings and real problems, which will come over in my presentation quite a bit, I think. So I'm going to talk about RAAC, is what I call it, RAAC, and I'll start introducing that in a minute. So we've been doing a lot of research in the last 2 years. What's the problem? I'll start with. We've got some big problems in the UK and other countries probably. We've done some research into it as a material and as a structural element. And I'll talk about some of the research and some of the structural risks, which is why the UK is so worried about RAAC. We've done some modelling and some monitoring, even some machine learning, artificial intelligence, crack detection. I'll mention that in a few slides. And then a bit about what to do with RAAC. How do we repair it? Can we repair it? Remediate it? Live with it is the term we use, living with RAAC. And then some further info, a few links, articles, if you want to go and read some more. So as an introduction, I think straight in, it's probably the first time our Prime Minister's been talking about concrete in the House of Commons. And the way I tell people, I've been working in concrete for 25 years and never been invited to any parties. No one's asked me about it or anything. In the last 2 months, my phone's ringing every day, emails galore from every news outlet, companies, different countries asking me about concrete. Even my friends are saying, can I ask you about concrete? It's gone concrete mad, which has been great for me. It's been very hard work, but concrete's been in the spotlight like never before. So it was schools, our concrete in schools, that kicked it off in the media. But before that, the same type of concrete in hospitals was in the news. A bit less so, but still in the news. Photos like this a year ago, props holding up the roof in hospitals. Obviously very concerned staff and patients. Is the roof going to fall in? When the focus moved to schools with similar images, the focus intensified because it was children. But it's not just schools or hospitals. It's almost any type of building from the 60s and 70s, 1960s, 1970s, which covers a large amount of the building stock. So it's not everywhere, but we describe it, it's in a very small amount of any type of building from the 60s and 70s. It's not just schools, it's not just hospitals, it could be almost any type of building from the 60s, 70s, which makes it very hard to find. So a quick timeline regards why we're worried about it and why it's in the news. This is a school from 2017-18. So this is actually 5-6 years ago. The whole roof collapsed. Thankfully, at the weekend, it was empty. No one was even there. No man hurt. There was a slight study. In hindsight, not a good enough study. Potentially shear cracks. You'll see the red circle there. Potentially a shear crack at the support. So potentially, because yeah, you're looking at the same photos we were looking at, potentially a shear crack, but not a thorough study wasn't really done. A year later, one plank fell down in the classroom. Again, empty, no one was hurt. One end came off the support. And so this is the main failure mode we're worried about. And to date, now we've gone looking, there's around 7 to 10 instances like this where usually one plank has fallen off somewhere in a variety of types of building. No one's been hurt yet at all, pretty much in empty buildings, and most of it's been caught by some other bit of the element. But we know now that these elements can fail and can fail without warning, although a very, very small proportion of them. But this is the concern, that they can fail with no warning, potentially fatally. So moving on to hospitals, we've been studying hospitals. So these are photos from a real hospital this year. It was on LinkedIn, which is where I got the photos from. A surveyor went in, concerned. You'll see their plank. That it's not a collapse, but it's failed. Failed by serviceability deflection, but probably by overloading. It's quite a typical failure mechanism. It's probably been overloaded from the roof. Someone's probably put something on the roof that shouldn't be there, overloaded it a lot. It's deflected, it's cracked, it's spoiling. And to be honest, it's almost been held together by the suspended ceiling and all the wiring and various other things hanging from it, which we do find is sometimes the case. So this is a failure, but it's bad practice. It was overloaded, and if it'd been made of timber, it probably would have failed. If it'd been made with another type of concrete, it would have probably failed. But it's RAAC, and it's in the news, so it's of interest. So that's a quick introduction why it's in the news. I think I need to explain what is RAAC, because you probably, like me, have been brought up on concrete, traditional reinforced concrete, which is everywhere, as we know. And that's what we teach at universities. That's what we build with, and that's what we understand. Concrete of about 30 megapascal, 40 megapascal. It's got a density of 2,400. It's got reinforcement in it. Every country in the world builds with it. Second most used resource in the world after water is what I tell my students. But RAAC is different. But the name's actually pretty good. So what is it? It's reinforced. So you see some photos there. It's got steel reinforcement, which is steel reinforcement, 500 Newton tensile steel. It's welded into a cage. It's got longitudinal tensile bars. It's got anchorage transfer bars that I'll come back to at the end that give it anchorage at the end, but it's steel and it's reinforcement. The unique bits are the autoclave, and that's a picture of an autoclave. It's a big pressure cooker to you and me. You might have one of these, a little one in the kitchen. So it cooks the concrete at temperature, about 200 degrees and under pressure. So basically increasing productivity. It makes it cure faster, gain strength faster, and hence you can produce more in your factory. Not rocket science, and it's been around 70, 80 years. So it's autoclaved. Aerated is the other bit. And this is something the media's latched onto. Look, it's aerated, it's all crumbly. Yes, if you get a knife and fork to it, you can dig away with it and make it crumble. It's actually got a compressive strength of about 3 megapascal, which is not very much, but it's fine because that's it's 3 megapascal. So when you're designing it, that's the number you put in, and you just make the element big enough. So the low strength is fine. Similar to timber. Some timber has a low compressive strength, but we're fine working with that. The strange one really is concrete because it's cementitious. It's got bog standard boring OPC as the main element to gain strength. It's got the sand in there, but it's no coarse aggregate. So really it's an aerated mortar rather than a concrete. There's no aggregate in there. And the magic ingredient is aluminium powder. which when you heat it up, it gives off carbon dioxide and creates those bubbles. Similar, I did at school. I remember dropping a bit of aluminium into some water in the classroom and it bubbled. Similar process, fairly basic chemistry. So there's nothing fancy in RAAC, but it is quite clever at the same time from a production point of view. So been around 100 years in Sweden. As I said there, sand cement, quite popular as is normal concrete, usually some form of slag or PFA in there, as well as the cement. Hydrogen bubbles, so I think that's a common. So it's hydrogen bubbles formed. The unique bit is how it's cooked or made in the mold. Because of the aerated, very low density. So if you're a builder, fantastic. This is half the density of water, a quarter of the density of concrete. You can pick up big pieces on your own. To build with is great. It's fast to construct. You need smaller foundations, a lighter supporting structure. Say a steel frame can be a bit smaller. MMC, I don't know if you use the terminology where you are, modern methods of construction, something we're obsessed with here in construction and in government, trying to force the industry to be more modern, to use more precast, prefab, modern methods, offsite, modular, whatever the terminology. We're trying to get the industry to be more productive and efficient. 100 years ago, this was the MMC of the day. Fantastic. And it's still used in many countries today. Because of the aerated nature, very thermally efficient. And economical, because there's not much cement in there, not much material in there. It's light, easy to transport, low carbon footprint. There's a long list of advantages of why this is actually a very clever material when you do it right. But then, as with any material, you have to do it right. And as we know from normal concrete is not always done right. There's so many structures around the world of traditional concrete that has corrosion problems, spalling problems because it was not built very well. The concrete was poorly specified. There's too much water in there, not enough cover. Every country in the world has problems with durability of traditional concrete. This has some similar problems because of the unique materials. They do manifest and play out in a slightly different way, which I'll come to. So I think I'm saying I'm not here to bash RAAC. I've researched it and know it very well now. It's a different material and it's very clever, but it's also susceptible to abuse. Because it's lightweight, you can cut it with a handsaw. And certainly if you have a circular saw, you can cut through the rebar because the rebar is typically 6 millimeters, 8 millimeters, maybe 12 millimeters at most. But circular saws, which you get on every building site, will cut through it really quick. So it does get abused a bit on site, which I'll come back to, and has been one of the problems. So I mentioned the reinforcement, and it's welded, it's smooth, and it's got a coating on. Because some of you might be thinking, oh, aerated, that's not going to keep the water out. That's not good for durability. And you're totally right. The AAC bit is rubbish at durability. Water can go in, chlorides, carbonation, it carbonates really quickly. So for protecting the steel, it's terrible. Well, we know this, and so we put a coating on the steel. So when it's made, the steel is dropped into a liquid slurry, a coating. There's a variety of coatings. Could be a cementitious, so a very higher strength, more concentrated cementitious sand cement slurry. Some of them are polymer modified. Nowadays, they're powder coating, so electrostatic coating to the reinforcement. They're put in the mold. You pour this slurry in. You put it in the oven. You autoclave it at high temperature and pressure, and the slurry expands due to the aerated nature. And we make it not in individual elements, and they typically come about 600 millimeters wide and about 200 millimeters thick as a typical cross section. So we don't make them in molds like that. We make them in very big slabs, like the photo there, called cake. They call it a cake. So they bake a big cake, which is really efficient for productivity. And then they cut it up. So they literally use a big cutter, often a wire cutter, like a cheese wire cutter, but on a big scale. And they slice up the big section into smaller panels. And then they might mill the edges, cut it to shape slightly, put some chamfers on, soft it, shape it slightly. So just to share some photos. So this is a manual from 1977. So it's been around a lot. 1977, you'll see several planks there. As I mentioned, 600 mil is the typical width. They come in various lengths and depths. So there's certain length to depth ratio to get your bending moment and structural capacity, but 600 is often the typical length. They can be supported on a variety of bearings. And I'll come back to this. This is often where the problem is. So you'll see a steel I-beam there. I think maybe about 100 millimeter flange. So when you've got 100 millimeters, if you build it perfectly, you've got 50 millimeters bearing that side and another 50 millimeters there. If you build it perfectly, and I used to be a contractor, I don't think I built anything perfectly to the millimeter. I was within 5 or 10 mil most of the time. But if you were 10 millimeters out, suddenly instead of 50 millimeters, you're on 40 millimeters. And then you've got the cover to the steel, maybe another 10 millimeters. So then you've got maybe 10, 20 millimeters where the reinforcement is going over your bearing, if everything else is done properly and well. So this is where the issue is, and I'll come back to this. So they can be on steel I-beams, can be on bricks, but similarly, if you're on a brick, and here's my brick, so you're on a brick, and a brick's that width. So again, kind of here's one I made earlier. So that's a brick, as you know, and we have a rack plank, and we'll have 2 of them. So that's sat like that. And if you build it perfectly, again, about 50 mil. But it's not always built perfectly. So what I'm getting at, if you do it all perfectly, you're sat on 50 millimeters of bearing for these planks. And I'll come back to whether we built everything perfectly in a minute. So that's how it's made and what it looks like and how it's built a bit. Where is it? So I said this at the start. It's in almost any type of building, but not many of them. It was very popular here from the 50s. We stopped using it in the early 90s because we were a bit worried about it then, so we stopped using it. Mainly floor or roof planks. So flat roofs from the 70s, very popular then. Schools, we have 22,000 schools in this country, and it's in about 200 of them, maybe 250. We found it in school. Healthcare, we have about 40 hospitals, and a lot of them have RAAC. In fact, many of them. We built a lot of hospitals in the 50s, 60s, 70s. Some of them have 10,000 planks in the roof. So imagine that the whole flat roof of a major hospital in a city, the whole roof is RAAC, 10,000 planks, and the walls. And so they have a lot of it, and a lot of it is not doing very well. And then you get an assortment of other types of buildings, shapes and sizes. And you'll see there 7 days ago, it's in the news on a daily basis. Somewhere finds it somewhere, and they find some. I mentioned they're still manufactured in many countries, expanding greatly in many, like India and China, very popular. You'll see Zeller is one of the leading companies. There's nothing wrong with the approach. I want to mention that again. If you do it well, like any construction, it can be very good. If you don't do it well, there's problems. And that's what I'll be talking about now, really. So Hence, what's the problem? If it is a good system, what's the problem? So I mentioned it was very popular here. There's some studies in the 90s at BRE, which is where I used to work, but I didn't do this myself. They tested some panels. They were deflecting a lot. They do creep more than normal concrete if you overload them because of the compressive strength. So they were deflecting more than normal concrete in some instances. So there's some studies there, and the advice was, well, there's nothing wrong with it really, but it does deflect more. And the kind of advice was, be very careful using it because it does have some problems. And so the industry moved away from it really in the country and stopped using it in the UK from the 90s. I mentioned, well, I showed the photos of the school collapse. That raised it up. We have something called SCOS here. You'll see there, Standing Committee on Structural Safety. This is where you report building failures for the good of the industry. So there's a report there, 2019, saying, you should go and find out where your RAAC is and have a look and check it's okay because it fell down in a school. So go and find it and have a look. The hospitals were already on this. NHS, National Health Service, is looks after all our health service and hospitals. They have a lot of RAAC. And the way I describe it is that hospitals are 24/7 buildings, as in they're occupied 24 hours a day, 7 days a week, with important people, patients, obviously, and staff, and therefore need to be open and maintained and operational. So their estates management, facility management teams know their buildings inside out, and their job is to keep it running. And so they know their buildings. They know every brick, every plank, every piece of wood, and they survey it and monitor it and keep it going. And they do a great job. So they were aware of RAAC and they were living with it and looking after it and maintaining it. But they thought in about 2021, we don't actually know much about it, and there's no guidance. There's no research being done on it, no guidance, and there isn't. There is a bit now, but 2-3 years ago, there was no information available. So they commissioned us to do some research on it, which I'm reporting on now. There's some guidance from the Institute of Structural Engineers, which we contributed to, and I'll mention that in a minute. And then this year came to the DFE, that's our Department for Education. They produced some guidance and school closures and immense interest from the whole of the industry and from government. But really, it was probably the SCOS alert that raised it in people's consciousness as something that needs special treatment. So moving on to the research we're doing or done in RAAC. There's some collaborators on the side there, funded by the NHS. So credit to them for putting their hand in the pocket, which is in hindsight proved to be a fantastic thing to do. They saved the country millions. We had some partners of SWECO, CPT, you might have heard of if you're into corrosion preservation technologies, leaders in corrosion of structures, and some testing partners there, Lucidium. So we did a variety of things, good concrete research of surveying where the rebar is, corrosion monitoring, testing. We did some SEM analysis, XRD, material characterization, structural testing of all planks, some modeling, finite element modeling, monitoring, data risk analysis, and some artificial intelligence on the surveying and the data analysis and things like that. But really, of the aim in the middle there, the ultimate aim was to understand how RAAC is different and how it behaves differently, because we can see it behaving differently. We can see it creeping, deflecting. We've seen it fail, but we don't know why. So in partnership with the National Health Service, better understand how we can look after the RAAC we've got. Grand title there, very, very proud to say this was a good example of iterative research informed practice, as in we did this very closely with industry, almost weekly conversations with the asset owner, NHS, weekly conversations with the IStructE who were surveying RAAC buildings and writing the guidance. And since then, daily, weekly conversation with government and other asset owners of what to do about it. That has informed the research, and the research informed the guidance, and very closely working together. Whereas typical research usually hides away for 2 or 3 years and issues a paper at the end of it that you're lucky if anybody reads. But this has been very, very close to practice and to government. And still, these 2 documents that are freely available online are still the 2 go-to documents for RAAC. The latest was in April, and it's still relevant and a go-to document. As well as that, I've written this, the university, national RAAC support. I've been coming back to the media, pulled in a million directions the last 2 months, talking to everybody from government departments, Scotland, Wales, Ministry of Defence, everybody, answering questions about RAAC. Lots of industry, too many to mention. You might recognise some of them there: Royal Institute Chartered Surveyors, Construction Leadership Council, Chartered Institute Builders, IC, Civil Engineers, blah, blah, blah. I talk about this daily, and I've answered every question there probably ever is about RAAC. And the media. The university said this was the biggest interest in a topic they've almost ever had. So, but I thought it was important to get the message about there's a lot of hysteria because hospitals, they thought hospitals and schools were collapsing, and they didn't open 200 schools. So there's a lot of public hysteria and worry there. So important part of the process to inform the public as well. But again, great to get the public interested in concrete. So going back to the research, we started by surveying hospitals who were paying for the research. So they survey their hospitals every year, if not twice a year, mainly looking for deflection and cracks, which is important. But we did it in more detail. We did thorough rebar mapping, exactly where is the steel in relation to the support and what condition is it in. We saw many issues of bad practice. Because this material is low compressive strength, you can core it and saw it very easily. And hospitals have progressed significantly in technology over the last few decades. When they were built, maybe 50 years ago, maybe you had a lighting cable running down the ceiling to turn the light on. That was probably it. Now, you've got everything from Wi-Fi, fire alarms, air conditioning, cable trays, suspended ceiling, more Wi-Fi, everything. And so the dead weight's increased, and the number of sockets and screws and box outs cut into it, skylights, water, electrical, they've really butchered a lot of it, and it suffered. And you'll see a photo from the middle where they core through some ventilation, and many examples where they pushed the steel reinforcement out of the concrete and just carried on and left it. So this is a very easy material to abuse. Then we did some structural testing. So partly in the lab, we took about 20 planks out of hospitals and tested them full size in the lab. Compressive shear testing, pull-out testing, bending. We also did some on site. So you'll see a live test on site there. That is bags of sand. So those are bags of 25 kilograms sand stacked up on one plank until it failed. So do you see the video there? So that's me in my boots. So that's one plank, 600 mil wide. Take off the waterproofing, and you'll see there, if you just jump up and down on it, it flexes quite a lot. So this material does creep, it flexes. It's fairly similar to timber as a material in many ways, rather than concrete. So we had quite low hopes of it taking much load, and partly because of the collapses we'd seen. But when we did load it, you'll see there, 92 bags of sand. The engineers amongst you, a very decent UDL load and a very decent load per meter squared, as in 2 or 3 times the design load. So it took 2 or 3 times the load it was designed to. So if you do it properly, this material is strong and takes a great load. So this was interesting. So well, what's going wrong? Why have some collapsed? Because the ones we're testing are actually doing very, very well. So the compressive strength I mentioned was very low, but we know that, and it was designed to be low, so that's okay. It actually has little influence on the structural capacity. If you change the compressive strength from 2 to 4 megapascal, the structural capacity, as in bending moments, doesn't change a great deal. It's the steel reinforcement that is the capacity and does the heavy loading. And one of our conclusions, we tested 40-year-old planks. We took them out of buildings, we transported them on the motorway, we craned them in the lab. They cracked a lot. They do crack quite easily. And we tested them. And even then, they took a good bending moment above what they're meant to from the design codes. So again, the planks themselves aren't too bad. Even after aggressive hydrothermal testing, so we put them in chambers, some of them, apply several days of rainfall, intense rainfall, accelerated weathering, temperature cycles, plus 40, minus 40, and their performance reduced slightly, as any material would in that aggressive environment. But still, they, in general, bar one plank, took enough load, even after that very aggressive hydrothermal testing. So I think we're probably surprised at this. So then you might be thinking, well, what's wrong with them? What's all the fuss about? So this is a hospital. This is a ward. So that's in the room. I've been in that room. No deflection, no cracks. Any surveyor would go in there and go, fine, no risk there. It looks great. But if you look on the photo, this is the outside, and we've taken off the fascia. That's a flat roof along the top, some waterproofing, and this is the end of the concrete panel sticking out the building with some plywood fascia on it. So we've taken the fascia off, and that's quite a deep 200 mil deep rack panel sat on a concrete ring beam. Okay, so not too bad, but you'll see there, you'll see some dots, and that's the steel sticking out the end. And you'll see almost some circles. So this is where someone's going to use a circular saw and cut off the end of the panel to make it fit the size of the room. Okay, but what they've done is they've sawn through the steel. And so what they've done is sawn through the end of the longitudinal steel. So you've got no cover. So in worst cases, then water can get to it, it can corrode. But the big problem, and this is where the main risk is, in some instances, they've not just reduced the length of the longitudinal steel, the anchorage transverse steel at the end that anchors those bars and stops them slipping all the way through, they've sawn off. So imagine the anchorage of those longitudinal bars, which take the bending moment, because the AAC is so weak, there's very little anchorage, very little at all. So they need these welded transverse bars at the end to anchor at the ends. Otherwise they slip through. And if you saw them off, you've got some bars there that can slip through when you increase the load. So this is the key concern. And this is the critical risk that we've seen in many different types of buildings. A small proportion, but critical. So it's not the fault of the rack as a material. This is where builders have cut the reinforcement off, which in any type of concrete is obviously a bad thing to do, but in particular for rack is very bad. So there's a photo of the inside of a rack panel. You've got the longitudinal reinforcement and transverse reinforcement. And it's the last bar that's important. You need that anchorage bar at the end to anchor at the end. And it's this zone near the support that we're worried about. So the guidance says that last transverse bar, anchorage bar, needs to be over the bearing. Because if it's not, then you've got no reinforcement at the edge of that bearing. And a shear crack can develop from the edge of that bearing into the plank. And that's a shear crack with no warning. There's no deflection warning. There's no initial cracking. It just cracks a shear crack, and it can collapse. And that's what's looked like has happened in some of the failures. So the really tricky thing is that you can have a room like this that looks perfect on the inside, but really there's critical reinforcement missing on the inside that you can't see. So this is the worry. That's the main worry. There's also a list of other defects that's in the guidance that can exacerbate this or accelerate it. So the main issue is the steel missing, which can lead to a shear failure with no warning. Some of these other defects can lead to that. Voidage around the reinforcement, deflections. If you've got your plank sat on your bearing and it's not very big, that's a problem. But then if you're deflecting, suddenly you've just developed a nice stress concentration at the point just where the crack wants to develop and propagate. So deflection isn't going to fail, but deflection can exacerbate the problem. And there's other defects that can exacerbate the problem. So you'll see there what I mean by the shear crack at the support, that top left. So we tested some in the lab and they failed like this at times. But again, at a fairly decent load. If the steel's in the right place, they can take some shear load and it's okay. But if that steel is missing, then we have a problem. So we developed some models and we had to develop our own, literally rewrite the code because this type of material doesn't exist in traditional finite element modeling programs, as in the compressive strength doesn't go low enough in the programs, and the granularity, the kind of quality or the finesse of the modeling wasn't fine enough to model exactly the bit that we want to model. So we developed some models that fit very well with practice. And we modeled this situation of the bar. So you'll see there, we've got the bearing support in blue, and we've got a plank over it with a UDL on. And we modeled this, and we moved that critical bar left and right. And you'll see the results of the top left. So if your bar is over the support, you've got enough shear capacity for the plank. The more it moves over the edge of the bearing, you get a reduction in shear capacity. It's not a binary yes, no. It doesn't go from being fine, you move it 1 millimeter and it's not fine. You get a reduction in shear capacity. But quite quickly, if you move away from the bearing, so that steel bar isn't over the bearing, then you start eating into your safety factor and your capacity too much. And then it depends on all the other factors, as in the loading being the main one, the size of the bearing, the condition, the quality of the AC, the compressive strength. If everything is perfect, maybe you've got a bit of leeway there. If you've got other defects in your structure, which many 50-year-old buildings have defects, then it could fail with that bar not very far from the bearing. So this is the key concern worrying the structural engineers, which very much informed the guidance and hence the closure of the schools. So we concluded the modelling was a good model. It validated with the full-scale results. You got a reduction in the shear capacity as the bar moves away. So that's the critical thing to find. And also that's the thing that's very hard to find. You can't just do it from visual inspection. And therefore, this rebar should be over the bearing to ensure your load capacity. And if it is, if that transverse reinforcement is over the bearing and you put a high load on it, you'll get a ductile failure, which is a safe failure. The more that bar moves away, the more likely to get a brittle shear failure without any warning. So, as any beam, if you load it enough, it is going to fail. So, coming back to my caveat and defensive rack, if the reinforcement's in the right place, then it will take a good load. But from the collapses we saw and site investigations, some of these bars are missing, mainly because they've been sawn off during construction, and occasionally they just maybe weren't there for manufacturing defects or modifications over its surface life. And mention about further research. So we get asked the question, well, okay, they've been there 50 years. So why are these planks failing now and not 10 years ago, 20 years ago, 30 years ago? We don't know exactly, which is why we need to do some more research. But our hypotheses are that cyclic damage, so climate change for me, so increasingly aggressive climate change, temperature changes, weather-induced rainfall is aggravating those planks more than ever before. Extreme actions, loads, just re-waterproofing your roof. You think you're doing a good thing, re-waterproofing it, but walking on it, several heavy men walking on one of these planks makes it deflect, creep, bounce, the grout comes away, and you've done it some damage. And also corrosion of the reinforcement, very much an unknown, because it's got this coating on, it corrodes in a very different way to a traditional reinforced concrete. So I'm just conscious of time. I'm going to skip through this part because it's less concrete technology, and also I didn't do it. And I'll finish up with a couple of summary slides about remediation repair. So what? What can we do about it? Deflection is the obvious thing we see. We can see it deflecting, and this stuff does creep and deflect. But it's more of a serviceability problem rather than a structural problem. It's okay if it deflects a bit. It might exacerbate this problem we have at the bearing, but it'll never fail from bending too much. So we can correct the deflection fairly easy. We can prop it up, but sometimes that makes it worse because you've aggregated or aggravated the plank. Spalling is a problem. Sometimes bits of concrete fall off, and hospital or school, this is the problem. Again, less of a structural problem. It's not going to fail because a bit of concrete's fall off. More occupant risk. Patch repair is very interesting. I think it's very difficult to do. There's very few patch repair products on the market, and compatibility is very difficult. Very different compressive strength and modular elasticity than the normal repair mortars. So your patch won't last long, basically. If you patch this with normal patch repair materials, it won't last long. Cracking, again, mainly cracking through deflection is what you see, and that's not really an issue. The shear cracking is the issue, and that's on the side of the planks, and you can't see the sides because they're next to each other. And if you're seeing shear cracking, sometimes it's too late because it's starting to fail in shear, and it's a bit too late. Corrosion, there is some corrosion in the roofs, but not enough yet to warrant structural reduction in capacity. There are some in exposed walls. RAAC is used in some hospitals on the walls, and they're not waterproofed. So these things have soaked up water for decades, and there's some quite serious corrosion on some of the walls. You can address that. Cathodic protection systems, sacrificial anodes, hybrid anodes have successfully shown they can stop that corrosion on the planks. But still, coming back to this, the main structural risk is this lack of a bar missing or two, and it's being cut off at the bearing support. That's the main thing. And so to remediate that, you can't put a bar back in. You need to strengthen it. So that's the main risk and main concern. So what have we been doing about it? What have all these schools and hospitals been doing to reduce this risk? And it's about reducing the risk. We can't afford to replace all the RAAC. There's too much of it. It's too expensive. So the main one is leave it and keep an eye on it. And many places are doing that. So the whole country's been finding RAAC and then keep an eye on it. The quick one is to put some props up, but they get in the way and they look bad and they scare patients and they scare children. So it's a temporary measure, really. So the main ones have really been end bearing supports. So this is where the critical risk is failure at the end bearing. So if you can apply some strengthening to the end bearing or strengthening and structural support to the whole plank, that reduces the risk. So you'll see there some very elaborate structural strengthening systems, timber or steel, that have been installed in many sizes of buildings. So there's a variety of these systems exist now. Or 5 and 6, replace it if you've got the money, demolish it. So again, it depends how long you want that building to operate, because many of these are 50 years old anyway. So some have just been, let's knock it down early, let's just leave it empty. Or if you want to keep it going, we install some repair and remediation. So just a couple more slides on further information. If you feel you want more webinars on RAAC, there's a few more there, past and present, slightly different angles. If you want some more, and I don't know if these slides have been circulated afterwards, possibly. If not, you can screen grab that. And if you want articles from us in the news, quite easy to find on Loughborough's website, where the history of RAAC, is it a problem, what's the issue, lots of information out there already. But I'll probably say that the main go-to place is the IStructE guidance. If you want to know more, that is still a very good summary document and the latest information. So I'll stop there. That's what I've covered in Introduction to RAAC. We've been doing some research on it. I missed out the modeling and monitoring for time, and then for more information. But happy to answer any questions. Please don't hold back on your questions.
Thank you, Chris. That was most interesting. And in very layman's terms, as usual, this seems to be a construction problem rather than a material problem. But the material suppliers are always the first ones to be blamed when anything goes wrong. So that's what we find in South Africa. I don't know if anybody in our audience can give us a feel for the application of RAAC in South Africa. Dr. John Roberts, do you have a handle on that sort of a number?
No, sorry, Anli. I can't answer that one.
Okay, but any questions? Chris has invited us. Anybody here that's got a question for Chris, please go ahead.
Speak up or type in the chat. All your questions answered.
Chris, with your permission, we've recorded the session. Can we put the recording of the session on our website?
Yes, but very happy to. And then
okay.
people can access the links and things like that.
Sure, that would be lovely. And if you would care to share your slides in a PDF format, we can most probably upload that. But please go ahead. Any questions? Chris, it seems like we've got no questions. I don't see any in the chat.
No.
So I think you're most probably off the hook for the moment. But may I just say thank you so much for being prepared to share with us at relatively short notice, but for a very interesting presentation. And don't believe it's the last time we're going to call on you. This is most probably just the beginning.
Yeah, please, if RAAC becomes an issue in South Africa and you want some advice or just want to ask where to go for some guidance, expertise, please drop me a line. And, very interested. I think there's a lot of countries now looking for RAAC. I went to a conference on AAC a couple of months ago. All the countries said, we don't have any problems with our RAAC. And which I responded to, well, you're saying your buildings that are 50 years old don't have any problems. And I said, oh, well, yeah. I said, well, you do have problems with RAAC. You've just not gone looking for it yet. And so I beg anyone to go look at a building that's 50 years old with a flat roof And has it been perfectly maintained? Was it perfectly built 50 years ago? Probably not. So I think the whole country is now looking for RAAC, and issues will arise from different countries.
Well, thank you, Chris, and thank you for this. Last chance for any questions. No, so we'll conclude the session. Ladies and gentlemen, this was our last CONCRETEFiX for 2023. We're hoping to resume our series of CONCRETEFiXes in the new year. Thank you for your attendance, and look out for the presentation that will be uploaded onto the website. A reminder, if you need CPD points for having attended this, make sure that Natasha's got all your EXA registration numbers and that she knows that you need CPD points. So all that remains for me to say is thank you again, Chris. Thank you for sharing with us. Everybody, have a super holiday time. Enjoy the rest that is a few weeks away, and see you all in the new year. Thank you. Take care.
Thank you, everybody. Bye-bye.
Bye, everybody. Bye.